Hello, my name is Christopher Glick. I'm starting my senior year in electrical engineering here at IUPUI. I'm going to tell you a little bit today about capacitor banks, but before I get started, I'd like to thank Dr. Dos Santos who invited me. I've spent the last 2 summers working for American Electric Power, a major Midwestern utility, as a co-op student, and they've given me ample opportunity to visit, test, measure, and design protection and control schemes for capacitor banks. Before I get started on the presentation today, I thought it'd be a good idea to first review a little bit about capacitors and active circuit elements. As you recall from physics, circuits 1 and 2, a capacitor is basically 2 electrodes, typically 2 plates with a dielectric between them. There's a positive and electric charge, or a negative charge on these plates. But the key thing is that the capacitor holds charge. That is to say, it holds voltage. The capacitor is an active circuit element, which means in an AC circuit, its impedance value has both real and imaginary values. The capacitor's companion is the inductor. The capacitor holds voltage, maintains voltage. Capacitor, or the inductor, maintains current. It is also an active element with real and imaginary components. A capacitor bank is nothing but a large arrangement of capacitors that can be connected in various combinations, series and parallel, to create the capacitance that's needed for a particular application. I'm going to show you a picture of a capacitor bank from some substation. I'm sorry if you're not able to see it well, but this is pretty much what they look like. In a substation, one particular thing I'd like to bring to your attention is that capacitor banks are arranged by phase. Right? Power is transmitted as 3-phase AC power. Now I know if you've taken circuits 1 or 2, you've gotten very little, perhaps no, 3-phase power. So I'm not going to spend much time talking about beyond hopefully to remind you that there are really 2 arrangements for 3-phase power. You can have the Y arrangement or the delta arrangement. In the case of a capacitor bank, each phase will have its own identical capacitor rack arrangement. Right? Now, why would anyone use a capacitor bank? It's an excellent question. There are 2 main reasons. One is to correct for power factor. The other is to boost local voltage. Now, I say correcting for power factor. If you recall from study of power, power is a complex number. It has a real and an imaginary component. Inductors, their imaginary component isn't positive imaginary. Capacitors is the negative imaginary. Power is voltage times current. In the case of power, then when you have complex voltage, complex current, impedance values, you get a complex value for power. And the real part of power is what we use. That's what the power company measures, that's what it sells, and that's what you use at home. That's what drives your equipment. Reactive power is there. I mean, it exists, but it doesn't really do anything. You don't get charged for it, but it's there, and the more reactive there is, in a sense, the less real. So what you want to do is correct the power factor. You want to minimize the imaginary component of power. You want to take that positive inductive part and offset it by the negative capacitive part so that the imaginary part goes to 0 when it approaches unity, leaving only the resistive power, the real power. I mentioned the inductive aspect because inductance is most consumer loads are inductive. The power that gets purchased by a factory is used to drive motors, for example, large powerful motors that introduce inductance to the system. at home, much of what you use power for is inductive, right? To power computers and household appliances. All these things are small, but in some, they contribute a large quantity of inductance that the power company thus wants to offset by introducing capacitance in the form of a capacitor bank. Capacitor banks are also pretty good at boosting local voltage. They don't boost it by more than 10% because exceeding 10% increases the stress on the capacitors in the bank, leading to a likelihood of failure and a possible chain reaction, and that's no good. All right. However, they can boost voltage by up to about 10%. Now, typically, power company wants to keep power supply within plus or minus 3% of the nominal value. But there are times when voltage sags occur, and often rather predictable ways. In hot summer days, in the afternoons, people turn on the air conditioners, and that sucks down a lot of voltage, and that draws down voltage for which bringing a capacitor bank online could compensate. Again, in the evenings, people come home from work, they turn on lights, they turn on the TV, doing things, and that creates, that adds an inductive load for which a capacitor bank can be very useful in offsetting that inductance. I've introduced here, showing here a description of a capacitor bank that I found on a schematic at one of the substations I worked at in the past summer. And since it can be a little bit hard to read, I'll read it for you. It says 16.2 mVar, 69 kV, 3-phase. That means 16.2 megavolts of megawatts of reactive power for 69,000 volt system that's 3-phase. The next line says 18 300 kVar, 19.9 kV, 1-phase. This means there are 18 300 kilovar, 19.9 kilovolt capacitors on any one phase. And since there are 3 phases, 3 times 18 means it's a 54 capacitor bank. Then it says fused units per phase and fused 15T, which means this is a fused capacitor bank with fuses per phase, and the fuses are 15T quality. I've attached here a roughly drawn distribution substation. Distribution is good for, it's good to illuminate what's going on because it's a very simple system. It's a one-way system. All the power flows in, as it does here. We got a 69,000 volt bus with a circuit switcher and a capacitor bank. The red arrow here is the 69K flow of power in. Right? Voltage comes in, travels along this bus to these guys, right? These distribution lines that run out to transformers that reduce the 69,000 to smaller and smaller voltages until you get a voltage that's waiting for you in the outlet in your house or factory. In the middle of this bus, a little bit above it, is a circle and 2 bars. These 2 bars are capacitors, and the circle represents a circuit switcher. And a circuit switcher is basically just 2 contacts. When those contacts come together, when they close, right, they bring the capacitor bank online. When the circuit switcher opens, the capacitor bank is taken offline. This is one example of a circuit switcher, SNC. This is the model 2030 that I've seen at some AEP distribution stations. There's a wide variety of these things out there. That would be interesting just to show one as an example. Well, how do you actually control a capacitor bank? This is done through the use of relays. Relays are devices that monitor current and voltage in particular, especially for capacitor banks, and other things as well, including impedance, often by taking the values on the system and reducing them to much smaller, proportionally smaller values so that electronic systems can measure and analyze those values. This capacitor bank does use fuses to protect against current, because a fuse is a very cheap way of protecting. Fuses respond to current. When too much current begins to flow across the fuse to the capacitor bank, or very rare cases from it, if something's gone wrong, the fuse will blow. When the fuse blows, it breaks the connection to the rest of the system, taking the bank offline, protecting it from current surges. If you have fuses, you don't need to install current relays that are monitoring current for controlling the capacitor bank. And often for distribution, you don't worry about current as it applies to capacitor bank. At higher voltages, it becomes more of a concern. Modern digital relays, right, are very fast, and they're much more precise than the old electromechanical relays that preceded them. There are still plenty of old electromechanical EM relays around, some dating from the 20s and 30s that I've seen and measured, but they're on the way out, right, in favor of digital relays. One of the greatest benefits of a digital relay system is that they're very easy to program in very complex routines to control a wide array of equipment and prevent for all sorts of eventualities. This is the SCL 351S, Schweitzer Engineering Laboratories. This is a very common digital relay for controlling capacitor banks. In particular because this model is quite adept at dealing with under and over voltage conditions. Under voltage being, for example, you set a particular value for this relay to watch for, and if the voltage on the bus, for example, drops to that value, this relay says, hey, circuit switcher, close in, bring the capacitor bank online, and thereby bring the voltage on tap back to normal. I'm coming to the end of my talk, so I thought I'd run through just a couple more things real quick before I wrap everything up. No matter the size of the capacitor bank, they always take 5 minutes to discharge. So if your circuit switcher pulls that capacitor bank offline and is immediately, followed by a voltage sag, you're going to have to wait 5 minutes before that capacitor bank can be safely brought back online. Capacitor banks, like everything, they can and do fail, but they're most likely to fail when they are brought online. When the circuit switcher or other device closes that capacitor bank in, current is going to flow. There's going to be a huge inrush of current into the capacitor bank. And the stresses and strains created by that inrush are what will lead to failure, most likely. And if one capacitor fails, the possibility is others will fail as well. And you get an ugly chain reaction that nobody wants. There are fused and unfused designs. Unfused designs are very uncommon below 34,500 volts. And this is simply due to the physics of capacitor bank design. I know that's quite a bit to run through in 10 minutes. But that's some review of basic concepts, especially regarding capacitors, what a capacitor bank is, what it's used for phase power factor correction, voltage supply, how they're a typical arrangement, how they're controlled, the types of relays. I suspect that all in all, nothing I've provided or nothing I've told you today was very shocking, but as capacitors do, I greatly appreciate the ability and the opportunity to discharge some of my experience so that you may benefit from it. Thank you very much.